Hello everyone, my name is Arip Asadulaev. I am a master student at ITMO University, and today I'm going to talk about my research related to conditioning of reinforcement learning agents and its policy regularization application. Firstly, I will give some highlights of our work, and then I will present some details of our proposed algorithms and experiments. Conditioning is a measure that indicates the proximity of the neural network to the dynamical symmetric property. Dynamical symmetry is a neural network property stating that the distance between network inputs is the same as the distance between outputs. The role of conditioning was studied for supervised learning problems, and it also was shown that conditioning regularization can help to avoid mode collapse problem in reinforcement in a generative adversarial networks. In reinforcement learning, the role of conditioning was not previously studied. In our work, we tried to answer the following question. Can information about a policy conditioning help to shape a more stable and general policy? To answer this question, we propose a very simple algorithm for conditioning estimation in reinforcement learning agents. Also, we studied the conditioning behavior on the different policies and proposed the conditioning regularization algorithm for proximal policy optimization and trust region policy optimization agents. Then we apply regularization to the coin run environment with a separated train and test levels to estimate the contribution of the conditioning to the generalization. Marcus Adena proposed a simple algorithm called Jakobyan clamping to compute condition number for the generative models. We adapted this algorithm for reinforcement learning agents, and before using conditioning regularization, we conduct a study of the relation between policy performance and conditioning to find justification for using it as a regularization. The goal of this test is to see that inefficient policies are less conditioning. In general, based on these experiments, a pattern can be observed. The policies that receive fewer rewards has a less optimal conditioning. Based on the previous observation, we propose algorithms that use condition number of the agent as a regularization. We apply regularization to trust region policy optimization and proximal policy optimization and compare their performance on the 8 continuous control tasks in a pi bullet environment. To regularize the policy, we simply use the values of the conditioning as a penalty. As we can see at the table, the regularized model outperformed basic variants in most of the tasks. Our continuous learning problems was set without explicitly separated training and test stage, and we can't estimate the contribution of the conditioning to generalization. In generalization experiments, we trained our model on a fixed large-scale set of the 500 levels in a coin run environment, and then tested model on some unseen previously levels. Our methods outperform PPO with other regularization as dropout and L2. In our opinion, extending the RL algorithms by conditioning regularization is a promising research direction. Condition number can provide important information about the policy, such as correctness of the hyperparameters and the stability. So let me now describe some details of our work. Firstly, let's describe the algorithm of conditioning estimation in more detail. To compute conditioning in reinforcement learning agents, we feed 2 mini batches at the same time to the agent. The first batch consists of the real environment states and some time step, and the second batch consists of the same states, but with some added noise, delta, to these states. And then we can estimate how the change affects to the agent output. After this, we compute the value psi that characterizes how close value g to the range lambda max and lambda min. These values approximately set the desirable range for the model conditioning. We save these parameters equal to the range defined previously for generative adversarial networks, and these values was equal to 1 and 20. If value g is inside this range, the value psi will equal to 0. The part of our experiments was done on a range of pi bullet tasks, and for each task we ran over 30 agents with different random seeds and different weight initialization. We analyze the behavior of the conditioning on the different policies that are set by different sets of hyperparameters and see the correspondence between the conditioning and the ratio of the achieved rewards. We ran proximal policy optimization with different hyperparameters and random seeds on the 4 continuous control tasks. We use the standard PPO parameters as an optimal configuration and made 3 adjustments to these parameters to produce a less effective policies. The example of the configuration presented in a table. Because of the environment dynamics, the linear relation between the reward curves and the conditioning curves is difficult to establish. However, the results show that conditioning often has a similar pattern with a number of the received rewards. To regularize the policy, we simply use the value of the conditioning as a penalty. On the slide presented a PPO total loss with added value psi to the surrogate policy loss. We conduct experiments of the regularization techniques on a PPO and TPO algorithms. We optimized agents over 5 million time steps. In this case, the hyperparameter setting is equal to the optimal one presented in a PPO and TPO literature for continuous control tasks. For TPO algorithm, we also use the mean conditioning of the trajectory as a penalty to the surrogate policy loss. We can see that regularized models often have conditioning closer to the 0 and collect higher rewards. Here is presented the other tasks, and we can see that conditioning regularization leads to the better performance on a 6 of 8 continuous control tasks. For generalization experiments, we run our method in a coin-run environment. Coin-run environment consists of many levels, where each level is different in a background color, but the task is still the same. Agent should collect some coins. And this level is separated to the train and test levels. And we run PPO with conditioning regularization in a couple with L2 and dropout regularization. We used the nature CNN and Impala architecture for this experiment. Our methods outperform vanilla PPO at all training scenarios. However, our work is still in progress. Our experiments show that different architectures, conditioning regularization produce various results. We plan to test conditioning contribution to the other architectures too and run them on environments like a DeepMind lab. Also, we plan to combine conditioning regularization with other state-of-the-art methods for generalization in reinforcement learning. Estimating conditioning directly using Jakobyan matrix and singular variable decomposition will be a very important experiment too. Thank you for your attention.